we are remaining. So like we will complete the kinetics part. We'll try to complete some part today and tomorrow. And Saturday, I wish to give you a free time so that you can check out your portion for various subjects and prepare for your session. Okay. Now, today you are having a mock test. Mock is for submitting. You got your undertaking, a copy of undertaking that you have to write in your own handwriting. Did you receive an email regarding mock?
Not yet.
Not yet.
1:45.
Yes, ma'am.
Acha, some of you have got like the prior intimation. A copy of undertaking might have been circulated to all of you, and you can keep the undertaking. You write it in your own handwriting on a A4 size paper. Put the date mock. Today's mock, so 27th will be your date to be put there, and like you can scan it and make a PDF of it. Okay, so that you can upload during the mock examination. So the most important part is the undertaking that has to be uploaded, and then mock test is just for your like to ensure like out of 96, even if one student find difficulty in joining and uploading, making a scan, he'll try to learn those things and try to ensure proper net connectivity. And so in that view, this mock has been kept. Now, mock most probably what all are your registered email IDs. With those which are there in the AIMS portal, they only will be operating. So you don't say at this time that this is my mother's email or father's email. Whatever is the email, ask them that this you have to see that part. Okay, because the what all is there in the AIMS portal, like exam section, we have to go with that. Okay, so coming to adsorption. Now, what we had discussed in adsorption was what is adsorption, what is absorption, what is sorption, what is occlusion, then what are the characteristics of adsorption, then what is physisorption, what is chemisorption, distinguishing features of physi and chemisorption. Then we saw Freundlich adsorption isotherm. Then we saw Lanier adsorption isotherm. The advantages and disadvantages or the limitations of both the isotherms we have seen. Okay, now we come to heterogeneous catalysis. Now, heterogeneous catalysis, the name itself indicates that you are using a different phased material, like your solid adsorbent is there and a liquid or gaseous adsorbate is there, and it works, the heterogeneous catalysis works on the principle of adsorption. Okay, so heterogeneous catalysis, like you have some particulate material acting as an adsorbent, you have a solvent, liquid, a molecularly defined catalyst is there, and the reactant molecules are there dissolved in this aqueous solvent. So these solute particles are there in the dissolved condition. Now you find that this is your heterogeneous substance. Now combination of homogeneous and heterogeneous catalysis can be there. Like you have a catalyst particle. This this is the solvent, and molecularly defined active sites are these red ones which are arranged here, and like the reactant molecules keep like are same as that on the bulk, as well as in the bulk of the solution, as well as on the surface of the catalyst. Now here you have an heterogeneous catalyst. In a heterogeneous catalyst, you are having a catalyst particle which is having over it the active sites, or there may be porosity in this catalyst and in the pores also the active sites may be there. So that is how the heterogeneous catalysis works. So this is the active site and these are the reactant molecules. So you will find that this reactant molecules get absorbed over this active site, call it as heterogeneous. So this is homogeneous and heterogeneous both together. This is heterogeneous catalyst. Different outcomes that can occur with a heterogeneous catalyst during a catalytic process. Like you have a reaction media, then you have a catalyst support. Heterogeneous catalyst is here shown, and these are the heterogeneous catalyst expected behavior that your uh, uh, feed reactors or the adsorbate will be adsorbed on the surface of catalyst, and because there will be high concentration of this on the surface, the rate of reaction will increase and the desired product is forming, and it is leaving, the product formed is leaving this particular thing. But when such reaction takes place, it is seen that there will be some undesired product formation also, which is shown by the green and the like this shaded balls. Okay, so heterogeneous catalysts that leach and participate in the reaction. So the catalyst itself, like small particles of it, are leaching out and are coming out with the product form. So such kind of reactions, you may call it as interferences, may be there. Now coming to heterogeneous catalysis, introduction is in heterogeneous catalysis, the reactants and the catalyst are in different phase. So catalyst is generally in solid phase and reactants are either in gaseous or liquid phase. Most of these catalysts can tolerate a wide range of operational conditions. One more reason for their wide use is that no additional step that is the potential energy here, shows that on adsorption, like due to like diffusion, the reaction, non-catalytic pathway, high energy is required. A catalytic pathway is the diffusion takes place and the various reactants arrange them on the surface of adsorbent, getting formation of leading to formation of a product and the product getting desorbed, and there will be change in the solute composition and concentration. So what is seen is here external diffusion of reactants takes place. The solute particles, solute A and solute B, go and adsorb on the surface of your catalyst. Now it may be the catalyst may be porous like this or may have less porosity. So internal diffusion of reactants take place and the adsorption occurs. Due to adsorption, the molecules adsorbed are closer, hence they interact with each other, forming a product. So once the product is formed, the product is diffused out from the pore or the active site or from the surface, and that is how your catalyst is regenerated and the film mass transfer of the product takes place or the product is removed from the surface of catalyst. Okay. Now there are different type of material. One class of material is metal organic frameworks. Now metal organic frameworks, this is the organic part and this central one will be the metal part. So a micro mesoporous narrow PSDs may be there. Designability, you can design this metal organic framework as you want. So they are excellent in design. Like you can design, or you can first go for computational work. Some softwares you can use to arrange those organic part and the metal part, so that, and then you can see whether it can work nicely. Then its crystallinity can be studied. Generally, such material has high crystallinity. Then they have little poor or good stability, depending on what is the organic part, whether it is poor or good will be seen. Then synthetic strategies are there. There can be a self-assembly based on which you prepare such metal organic frameworks, or based on dynamic coordination, bond formation. You can prepare this. PSM methods are there. So summary is highly developed, and it can be efficient with and without co-catalyst. So it can work. So such substances work as a heterogeneous catalysis. Then another type of material that works as heterogeneous catalyst is covalent organic frameworks. So there can be, this is metal organic frameworks, these are covalent. So two or more organic molecules are taken in proper proportion and they are allowed to self-assemble or under certain condition, and you get formation of this. Now here we can see they have good, like you can design as per your requirement. You can take like some nitrogen containing and some like hetero containing, or functional molecules like having double bond, so that the pi bond breaks and the required structure can be made. So imines and triazines are mostly used in such compounds. Then you have amorphous porous organic polymer. So some organic polymers which are amorphous in nature, your polyvinyl chloride, then your uh, like sulfonic acid, as we have discussed in uh, ion exchanges, right? Instead of sulfonic acid, you may have number of other things in the polystyrene backbone or polyvinyl chloride backbone. You can add certain functional groups, and that can work. So they are amorphous in nature, and they are organic polymers. Then you may use a nanoporous ionic organic networks. So they are nanoporous, means they have porosity, and this porosity is determined by performing BET studies, that is Brunner, Emnet, and Teller studies for nitrogen adsorption. So the porosity can be determined using that. So you prepare. So these are classed based on their chemical composition. Okay, and these can be used as heterogeneous catalysts. Now you can have an high activity catalyst and a low activity catalyst. Now high activity catalyst will have uh, certain it has ability or certain specific sites, so that it can absorb number of different species of uh, adsorbate molecules, or different type of gases can be absorbed. A low activity catalyst does not have ability to absorb number of gases, only those which are easily liquefiable, or are gases at like remain gas. So such type of material only can be absorbed. So such catalysts exhibit low activity. Okay. Then there are certain catalysts which show high activity, are like have, uh, here it is shown that this is having ability to take up these, and here you see this has been removed. Then higher activity, like this is the part where the particle size has been So you pulverize the thing and then use it. So greater surface area will be available. And if you don't pulverize it, if it is a larger lump, then you will have lesser ability to take this. So uh, some similar principle can be used like the lump if it is having ability. Now here you can see this is not mono-layer formation like over each another like the residual forces are being compensated. So such type may show higher activity. Then you are having certain active site and certain inactive site. So here it is shown separately. You may have on a single surface, say two active sites, two inactive or one passive site. So the number of active sites should be more, and the number of passive sites should be less. So these active sites should be more. So here you can see that this is the catalyst, this is the reactant, this is your activator. Here the activator is used and the green one is the inhibitor and this is the modified catalyst. Okay, so they have modified the catalyst in such a way, modified activator is there, and these are the modified activators, and this is the modified inhibitor, and that is how the process of this one is taking place. Okay. Then examples of heterocyclic catalysis. Reductions of nitriles, for instance, in a synthesis of phenylethylamine with rallying nickel and ammonia. The cracking, isomerization, and reforming of hydrocarbon to form appropriate and useful blends of petrol. Okay, there you use a catalyst. Then catalytic converters are often used in automobile. The main reactions are catalyzed by catalytic converters. The oxidation of carbon monoxide to carbon dioxide. So we see carbon monoxide, that is incomplete combustion of carbon or oxidation of carbon is made to convert completely into carbon dioxide. So complete oxidation of carbon monoxide because carbon monoxide is highly toxic. Okay, so that is done in the catalytic converters. In the automobiles, you have two chambers. One is oxidation, and another one is reduction. So in the oxidation chamber, palladium catalyst is used, where carbon monoxide will be converted to carbon dioxide. Okay. Then reduction of nitrogen monoxide back to nitrogen takes place, and this takes place in the reduction chamber. The oxidation of hydrocarbons to water and carbon dioxide takes place, and this process can occur with any of the hydrocarbons, but most commonly is performed with petrol or diesel. Asymmetric heterogeneous catalyst affords enantiomerically and enriched compounds using chiral heterogeneous catalyst. The vast majority of heterogeneous catalysts are based on metals or metal oxides. However, some chemical reaction can be catalyzed by carbon-based materials, that is, oxidative dehydrogenation or selective oxidation. Example is ethyl benzene plus half O2 giving you styrene plus H2O. Acrolein plus half O2 giving you acrylic acid. These are the two reactions. Gas streams with a strongly non-equilibrium gas phase concentration can be achieved via epicatalysis. Epicatalysis is another term. Okay, so catalytic reactions may involve oxidation, like synthesis of terephthalic acid from xylene using ZSM5. Okay, so ZSM5 is the catalyst, that is zeolite soponimobile. Okay, so that's the ZSM5 it is written here in short. So it is prepared by oxidation of paraxylene using ZSM5 as catalyst. zeolite soconi mobile. So that is ZSM5 as catalyst. So the single step reaction is as like you have paraxylene in presence of catalyst, you get formation of terephthalic acid, and you get back the ZSM5. Then next one is uh, reaction involving reduction. So hydrogenation of alkene to alkane using Raney-Nickel catalyst. In this reaction, the hydrogenation of CC double bond takes place, and just excuse me. Of alkene to alkane using Raney-Nickel catalyst. In this reaction, the hydrogenation of C double bond C at the surface of catalyst results in addition of hydrogen. So this is your ethylene H2 in presence of Raney-Nickel, get formation of ethane. Okay, then catalytic reaction involving cyclization, benzimidazole synthesis using orthophenylene diamine and benzaldehyde by solid acid catalyst. The benzimidazole can be synthesized by cyclization of orthophenylene diamine and benzaldehyde in presence of various catalysts. Okay, so catalysts like acid support or clay solid support, amber light or ammonium chloride catalyst. So you have different type of catalyst. One of the method used for synthesis of benzimidazole is shown here. So this is the orthophenylene diamine. This is benzaldehyde, and these are the catalysts giving benzimidazole. So, what are the advantages of heterogeneous catalyst? Catalyst is regeneratable, or you can regenerate the catalyst, avoid formation of inorganic salts, easy to handle, it is non-toxic, safe to store, long lifetime, and easy and inexpensive. Okay, so these are some of the advantages of heterogeneous catalysis. So with this, we complete the heterogeneous catalysis part, and now we will move to kinetics because we should complete the kinetics portion also by Friday. Okay, so
In this, inorganic salts are not formed.
should not be formed like you take because that will contaminate your catalyst, right? And so if it is like that, then it is better. It is avoid if it is possible to avoid, you can avoid. I mean, take precautions to avoid that. Okay, coming to the chemical kinematics or chemical kinetics. Can you see the screen? Uh, Yes.
Yes, ma'am.
The chemical kinetics you have already studied for your uh, JEE and 10th standard, but since it was all online, we will again see all those things. Now, what we are supposed to read is Introduction to Rate Equation and Reaction Order, reaction mechanism, relation between rate equation and reaction mechanism, first order and second order reaction, dependence of temperature on reaction rate, and the Arrhenius theory. This much only you are supposed to read. There is no inclusion of your collision theory and other theories. Okay. No, collision theory and transition state theory is there, but the consecutive reactions and chain reactions, this part is not there. Okay. So coming to the contents, rate of chemical reaction, that is termed as rate law, order of chemical reaction, the order of different chemical reactions with examples we will see. Then what is molecularity and how it is different from order. Then factors that affect reaction rate. Then Arrhenius theory, collision theory and transition state theory and the numericals based on this part only. Okay. So what is the reaction rate? How we measure the rates? Rate law, how the rate depends on amount of reactants. Then integrated rate law, how to calculate amount left or time to reach a given amount, maybe in percentage or a given amount. Then half-life is how long it takes to react 50% of the reactants. And Arrhenius equation, how rate constant changes with temperature. And mechanism, it links link between rate and molecular scale process. Okay. So introduction, chemical kinetics, also known as reaction kinetics. It is branch of chemistry which is concerned or deals with uh, the reaction occurs in how many steps, whereas thermodynamics tell you whether the reaction will take place or not, but this will tell you how the reaction is proceeding. So chemical kinetics include investigation of how experimental condition influence the speed of chemical reaction and yield information about mechanism of reaction. What are the transition states involved? Then as well as the construction of mathematical models to describe the characteristic of a chemical reaction. So thermodynamics does a reaction takes place will be told to you by thermodynamics. Feasibility of the reaction will be told by thermodynamics, but how slow or how fast or one step fast, rest are slow, or one is slow and rest are fast is told by kinetics. So kinetics studies the rate at which the chemical process occurs besides formation information about the speed at which the reaction occurs. So here you are having reactants. The reactant concentration goes on decreasing and the product formation or the uh, number of molecules of product form with time it goes on increasing. That is what is shown in this particular figure. Definitions of the terms. Rate of reaction. Reaction rate is the change in the concentration of a reactant or a product with time. So A is your reactant converting to B product. So because the concentration of reactant is decreasing, there is a negative sign. So rate is equal to minus change in the concentration of A with respect to time, change in time T. Similarly, because product is forming, it will be positive. So the rate is equal to del V concentration by changing in small change in time T. Okay, delta T time. So because A concentration decreases with time, delta A is negative. So then the rate law. Now the rate law expresses the relationship of the rate of reaction to the rate constant and concentration of the reactants raised to some powers. The mathematical relationship of reaction rate with reactant concentration is known as rate law. This relationship may rely more heavily on the concentration of one particular reactant, and the resulting rate law may include some or all or none of the reactant species involved in the reaction. For the following hypothetical reaction, A number of A reactant plus B number of B reactant giving you C, the rate law can be expressed as rate is equal to K into concentration of A raised to Y and B raised to Z. Okay, the proportionality constant K is known as the rate constant and is specific for the reaction known shown at a particular temperature. The rate changes with temperature and its units depends on the sum of concentration terms exponents, sum of the exponents of the concentration term in the rate law, that is y plus z. So the exponents y plus and z must be experimentally determined and do not necessarily correspond to the coefficients in the balanced chemical equation. So the rate expression and rate constant. So the rate of a reaction decreases with the passage of time as the concentration of reactants decreases. So the rate of reaction depends upon the concentration of reactants. So here A plus B giving you C plus D. Here A, B, C, D, small a, B, C, D are the stoichiometric coefficients of reactants and products. The rate expression for this reaction is rate is proportional to concentration of A raised to X and concentration of B raised to Y. So the product of the concentration of the reactants raised to the exponents x and y. Now, what are the exponents x and y? May or may not be equal to a and b, the stoichiometric coefficient a and b. So, this is important that they may not be same to your stoichiometric coefficients a and b. Above equation can also be written as the rate is equal to rate constant k into the concentration of a raised to x and b raised to y. Differential rate equation and rate constant. The differential rate equation, this form of equation is known as differential rate equation, that is dr by dt, that is your reactants, is equal to the rate constant k into a raised to x, b raised to y. The rate law is the expression in which reaction rate is given by terms of molar concentration of reactants with each term raised to some power which may or may not be the same as stoichiometric coefficient of the reacting species in a balanced chemical equation. Some examples are given below. Reaction experimental rate expression. Twice NO gas combines with oxygen forming twice NO2 gas. So here the rate is equal to K rate constant into the concentration of NO raised to 2 into the concentration of O2 gas. Second example is chloroform CHCl3 plus chlorine gas giving you carbon tetrachloride plus HCl. Now here the rate is equal to K into the concentration of chloroform into the Cl2 raised to half. So here you can see it is raised to half. So it is not necessary that the stoichiometric coefficient may be same as that in the rate law. So elementary reaction and molecularity. What is an elementary reaction? A balanced chemical equation never gives us a true picture of how a reaction takes place, since rarely a reaction gets completed in one step. The reaction taking place in one step are called elementary reaction. When a sequence of elementary reactions called mechanism gives us the products, the reactions are called complex reactions. The number of reacting species, atoms, ions, or molecules taking part in an elementary reaction which must collide simultaneously in order to bring about chemical reaction is called molecularity of the reaction. Depending on how many molecules come together, a reaction can be unimolecular, bimolecular, or trimolecular. The kinetic order of any elementary reaction or reaction step is equal to its molecularity, and the rate equation of an elementary reaction can therefore be determined by inspection from the molecularity. Okay. Then rate law and elementary steps. For unimolecular reaction, a reactant gives you product. So rate law will be written as rate equal to K into concentration of A. For a bimolecular one, it will be rate equal to K concentration of A into B. Then a bimolecular reaction where both the molecules of are same type or same reactant, A plus A, giving you product, it will be A square. Okay. So order of reaction. Now what is order of reaction? It is the sum of powers
Previous
of
slide, please, ma'am.
concentration terms. Yes.
Previous slide, ma'am.
Pardon?
Previous slide, ma'am.
Yes.
Okay.
Okay. Order of reaction. So what is order of reaction? The sum of the powers of concentration terms in rate equation is known as order of reaction. You may also call it as order of reaction may be given with respect to all participating reactants, in which case it is called order of reaction. The mathematical expression showing the dependence of rate on the concentrations of reactants is known as rate law or rate expression of the reaction, and the sum of indices, that is powers of the concentration terms appearing in the rate law as observed experimentally, is called order of reaction. So here we see that for a reaction A plus B giving you C plus D, the reaction is mth order in A and nth order in B. So rate law can be written as rate equal to K into concentration of A raised to M and B raised to N. So the order of reaction becomes M plus N, M plus nth order overall, or mth order with respect to A or nth order with respect to B, or the overall order is m plus n. Then comparison between molecularity and order. Molecularity represents the number of reactant molecule taking part in a elementary reaction. Order represents sum of exponents to which concentration terms in the rate law are raised. It is theoretically Molecularity is a theoretical property and indicates the number of reactant molecules involved in each act leading to the reaction. Order of reaction is an experimental property and indicates the dependence of observed reaction rate on the concentration of reactants. Molecularity is always an integer and can never be fraction or zero. Order of reaction may be an integer, fraction, or zero. Molecularity is the property of only elementary reaction and has no meaning for complex reaction. Property, order of reaction is property for both elementary and complex reaction. Okay. So coming to the zeroth order reaction kinetics, a zeroth order reaction is one whose rate is independent of concentration. Its differential rate law is rate equal to K. We refer to these reactions as zeroth order because we could also write their rate in a form such as A concentration raised to zero, that the exponent of the reactant in the rate law is zero. So A is the concentration of A at any time t, and A naught is the concentration of A at time t equal to 0. So t equal to 0 means it is the initial time, or we say A naught is the initial concentration and A is after, or A t many people write after time t. So A minus A naught is equal to KT. Okay. So this is half-life for zero order reaction. T half is given as T when A concentration is equal to A naught by 2, or you can write P half is equal to A naught concentration of A at 0 time by 2K. Okay? And the graph that you get is for time versus concentration of A, that is A versus time plot, you get K value from the slope, and the slope is negative. You get a negative slope for K. Then for a plot of natural log of concentration of A, that ln concentration A versus time, you get a hyperbolic curve. And for a graph of 1 by A concentration versus time, you get uh, a curve of this type. Okay, so examples of the reaction uh, that are zero order kinetics, or which follow zero order kinetics, are uh, like the reaction of hydrogen with chlorine. It's a photochemical reaction in presence of sunlight or H nu, a specific energy photon. You get formation of, from H2 gas plus Cl2 gas, you get formation of HCl gas. Then decomposition of nitrous oxide over a hot platinum surface, on in presence of hot platinum, nitrous oxide N2O forms N2 plus O2. A zeroth order reaction that takes place in a human liver is the oxidation of ethanol from alcoholic beverages to acetaldehyde, catalyzed by the enzyme alcohol dehydrogenase. Okay, so one example of biological entity has been made. At high ethanol concentrations, this reaction is also a zeroth order reaction. So ethanol plus NAD in presence of, like the, of course, the alcohol dehydrogenase is the enzyme which will convert this into CH3CHO. Okay, so that is acetaldehyde or an aldehyde, and aldehyde plus NADH plus H plus. Okay, so this is the reaction for that. Okay, I think we will stop here. The first order kinetics we will see. Tomorrow is Friday. Okay, so I think I'll take the class and complete the syllabus tomorrow. How many of you are listening to me?
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am.
Yes, ma'am. Yes, ma'am.
A lot many things are there to discuss. We will see this tomorrow morning. But I have MSc class also tomorrow. So anyhow, the zeroth is over. The first order is remaining. We will see this tomorrow. Now, is there anything from your side? I told you. Can you hear me?
Yes, ma'am.
Yes, ma'am.
Ma'am.
Okay, I told you for X2 batch some students only are remaining. I'll take your Viva after session. We will see that part. And by tomorrow, I will try to finish the kinetics part. So if I am able to finish the kinetics part tomorrow, then I will not engage Saturday morning class, and I will keep one only a 10-mark MCQ test on Saturday. Sometime I'll inform you on the WhatsApp group. So you will receive the link in your email, so that like what all uh, uh, queries you develop after getting the solution and all, that will just brush up your things for your sessional exam also. Okay. So a 10-mark theory test I'll